Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. We're happy to have Shayan Oveis-Garan from Stanford to tell us about spectral graph algorithms.
Hello. Hello, everyone. Thanks for inviting me here. It's very good to be around. So I want to talk about new analysis of spectral graph algorithms through higher eigenvalues. Okay. Okay. Suppose we have a set of data points. Okay. And we want to cluster them. Okay. One way to do the clustering is first to construct a graph based on these data points, and then use a graph partitioning algorithm. Okay? How can we construct a graph? First, we put a vertex for each of the data points. Now here I connected two vertices if their distance is less than a threshold epsilon. Okay? So there are also other ways to construct a graph. For example, you may construct a complete graph, a complete weighted graph, where the weight between each pair of vertices is a function of their distance. Okay, for example, you may use this function, e to the minus distance squared over normalized by some constant sigma. Okay? So once we constructed the graph, we want to partition the graph. So how can we partition this graph? We can use a spectral graph partitioning algorithms. Okay? So first, we compute multiple eigenvectors of the graph, say v1 up to vk. Then we use these eigenvectors to embed this graph in a k-dimensional space. So basically, what we do is that we construct this matrix F, where the columns of the matrix are the vectors v1 up to vk. Now, the rows of this matrix would give me the coordinate of the vertices. So the coordinate of vertex I would be v1 of I, v2 of I, up to vk of I. So this gives me a mapping of my graph to this high-dimensional space. Maybe for the graph I showed in the last slide, this is the embedding. Now I can use one of the heuristics, for example, k-mean, to partition the vertices in this high-dimensional embedding. And that basically gives a partitioning of my graph. So putting this all together, we get the spectral clustering algorithm. Okay? So let me summarize it again. We start from data points. Then we construct a graph. Then we look at the eigenvectors of the graph, and we embed it in a high-dimensional space. Then we apply k-means, partition these vertices, and we use that to get a partitioning of the original points. Just map it back to the original data points. Okay? So the spectral clustering has been used for over 20 years. It has a lot of applications. I chose this particular paper, Eng, Jordan, and Weiss, because this is one of the very famous papers in this direction. Okay? So is this clear? Good. In general, spectral graph algorithms are simple heuristics that explore graph structure using several eigenvectors of the graph. Okay? These algorithms are widely used in practice because of the following reasons. First of all, they're very simple to implement. If you have a linear algebra library, you can simply implement them. They provide very high quality solutions, usually, and they run very fast. They run usually in near linear time. Okay? Here are some applications. For example, I talked about applications in data clustering. You can also use them in image segmentation, community detection, VLSI design, and many other fields. So for example, in image segmentation, what you do is that you put a vertex in a graph for each of the pixels in the image. And then the weight of the edge between a pair of vertices is the function of the distance of the pixels and how close their colors or their intensity are. Okay, and then you partition this graph and you get a segmentation of the image. Okay? Now let me tell you what we know about spectral graph algorithms in theory. Classical analysis of spectral graph algorithms only exploit the first or last two eigenvalues of the graph, eigenvalues or eigenvectors of the graph. Okay? Here are some examples. For example, Wilf's bound on the chromatic number of a graph, Cheeger's inequality, the algorithms for finding edge separator of a graph, even the algorithms for finding maximum cut. There are many others I'm going to say later. But all these algorithms only use the first or last two eigenvalues. Okay? I should mention that in some random or semi-random models, we know algorithms that use matrix perturbation theory and multiple eigenvectors. But here, I do not assume anything about the graph. I mean, the results will be unconditional. Okay? So let me summarize what I said so far. Let me put theory and practice together. So I said in practice, we typically use multiple eigenvectors, and more eigenvectors give better solutions. In theory, we can analyze two eigenvectors or two eigenvalues and show that they give good results. Okay? Now let me tell you what we do. So basically, we analyze or study the spectral graph algorithms through the lens of higher eigenvalues. Okay? So you can see our result as a bridge between theory and practice. So let me just give an overview of the results without giving into details at this point. So for example, we relate the kth eigenvalue of a graph to k-way partitionings. We can use higher eigenvalues to justify the performance of spectral algorithms in practice. We can also use higher eigenvalues to even give faster spectral algorithms. Okay? Now, if you want to see the actual quantitative version of this result, you should give me some time that I set up some notations, and then I'll give the details. Okay? So here is what I'm going to do. I'm going to start by talking about Cheeger's inequality. Okay? Here I'm going to set up some notations, and then I will focus on our results. I will talk about these three results. And finally, I will very briefly talk about other aspects of my research and some future direction. Okay, is there any question at this point? Okay, so let me start by talking about Cheeger's inequality. So for the next 5 minutes, I'm going to define the Cheeger inequality and set up some notations. Okay? Let L be a normalization of the adjacency matrix of a graph. This is also known as the normalized Laplacian matrix. Let me not define it rigorously, but the point is we just normalize the entry corresponding to each edge of the graph by the degree of its endpoints. Okay? We use this normalization to basically normalize the eigenvalues to fit in this constant range between 0 and 2. Okay? So this gives us a normalization of the eigenvalues. So throughout the talk, I'm going to use lambda 1 up to lambda n as the eigenvalues of this normalized Laplacian matrix. Okay? Lambda 1 is always 0, lambda n is always at most 2. Okay? Now, there is a basic fact in algebraic graph theory which says that lambda 2 is equal to 0 if and only if the graph is disconnected. Okay? Now, Cheeger's inequality gives a robust version of this fact. Okay? You can imagine what it would say, right? It would say lambda 2 is very close to 0 if and only if the graph is barely connected. But to give the actual quantitative version, I need to define a robust version of connectivity. Okay? So let me do that first and then give you the Cheeger's inequality. Okay? So what is a robust version of connectivity? I'm going to use conductance as a robust version of connectivity. Okay? So the conductance of a set S of vertices is the ratio of the number of edges leaving the set to the sum of the degrees of vertices in S. Okay? For example, in this picture, the conductance of this set is 1/8. because 2 edges are leaving the set, and the summation of vertex degrees is 16. Now, conductance is always a quantity between 0 and 1. You can easily show that. And the point is, the closer to 0 means that we have a better cluster. Okay? For example, if the edges of the graph represents friendships in a social network, then a set with a small conductance would represent a community in the social network. Or if the edges of the graph represents the similarity between data points, then a set with a small conductance would represent a cluster of data. Okay? So the sparsest cut of the graph is the set with the smallest conductance. We're going to choose it among all of the sets that have at most half of the vertices or half of the vertex degrees. Okay? So I'm going to use this parameter phi of g as the set with the smallest conductance in the graph. Okay? Now I'm ready to tell you the Cheeger's inequality. So Cheeger's inequality for graphs is proved by Alon and Milman'. And it says the following. For every graph G, phi of G is very well characterized by lambda 2. It is at least 1/2 of lambda 2, and it is at most root 2 lambda 2. Okay? So let me tell you how you should read this. You should read this as follows. G is barely connected if and only if lambda 2 is very close to 0. The importance of this inequality is that it is independent of the size of the graph. So no matter how large your graph is, you still get the same characterization. The proof of this inequality would give you a simple linear time algorithm. And in fact, it shows that the spectral partitioning algorithm for graphs would work if k is equal to 2. If you just want to partition your graph into 2 sets, you use a second eigenvector, it would work, and it would give you a set of conductance at most a square root of phi of g. Okay? Good. So let me tell you some applications of this inequality. Cheeger's inequality is one of the fundamental results in the spectral graph theory. It has applications in various fields of computer science. For example, in algorithm design, many of the approximation algorithms use this inequality, or algorithms that looks for a separator of a graph. There is a whole literature in probability theory that use Cheeger's inequality to analyze the mixing time of random walks. And you can use this inequality to design algorithms that can sample from very sophisticated distributions. There's also many applications in the complexity theory and cryptography. For example, in constructing expander graphs or in error correcting codes. Okay? Okay. Now that we all understand Cheeger's inequality, let me tell you our results, our contributions. So as I said, we analyzed the spectral graph algorithms with a theme of higher eigenvalues. In a joint work with Lee and Trevisan, we prove a higher order variance of Cheeger's inequality. We basically relate the conductance of cuts in k-way partitionings to lambda k, the kth eigenvalue of the normalized Laplacian. This will provide a rigorous justification of the spectral clustering algorithm that I described at the beginning of the talk. Okay. In a joint work with Kwok, Lee, Lau, and Trevisan, we managed to improve Cheeger's inequality using higher eigenvalues of the graph. And this gives us a rigorous justification of the performance of the great performance of a spectral partitioning algorithms in practice. Also, in a joint work with Trevisan, we design fast local algorithms for finding small communities in social networks. This basically gives an algorithm with the same guarantee as of the spectral partitioning, but with the advantage that it can be run in sublinear time. Okay? So I'm going to basically talk about these three results. And I'll spend most of the time talking about the first result, give you some ideas, and then I'll talk about the last two. Okay? So next I'm going to talk about high-order Cheeger inequality. High-order Cheeger. Okay, so for the next 10 to 15 minutes, I'm going to talk about this result and then talk about the last two. Okay. So here, we want to study the following problem, K-clustering problem. Okay? So we are given an undirected graph. It can be weighted, but let me assume it's not weighted to make it make notation simpler. We want to determine K disjoint clusters, S1 up to Sk, of a small conductance. All right? So for example, if this is our graph, maybe we find these clusters. Their conductance is as follows. Now, the quality of this clustering is just the worst conductance of these sets, just the maximum conductance of these sets. Okay, so here it's 2/8. All right? So in general, if we find a clustering into S1 up to Sk, we define its quality as the maximum conductance. And our goal is to find a K clustering whose maximum conductance is as small as possible. Okay? So the optimum is the clustering that achieves this. And I'm going to use this parameter phi of K for the optimum. Okay? So again, phi of K is a K clustering whose maximum conductance is as small as possible. So let me tell you what we prove. In a joint work with Lee and Trefison, we show that phi of K is very well characterized by lambda K. This proves the conjecture by Miklo. The point is, here, similar to Cheeger's inequality, there is no dependency to the size of the graph. So no matter how large the graph is, still you get the same characterization. There is a dependency to the size of the clustering, K, but not to the size of the graph. Okay? Let me show you an example to understand this better. Say our graph is just a cycle. Okay? What is a K clustering of a cycle? Basically, all you need to do is to find K disjoint paths, each of length about n over K. Okay? This is the best we can do. And therefore, phi of K will be K over n, because the conductance of all these sets will be about K over n, or 2K over n. Okay, so this phi of K will be about K over n. Lambda K will be about K over n squared for a cycle. So putting these two together, you see phi of K is less than root lambda K. We don't even have a dependency to K in the right-hand side. Okay, is this clear? So what else do we prove? We show that if we are allowed to use 2k eigenvalue, lambda 2k instead of lambda k, then we can significantly improve the dependency to k from k squared to root log k. And if the graph is low dimensional, it's a planar bounded genus graph, we can completely get rid of dependency to k. Okay? So the second result here, a weaker version of the second result is proved by independently by Lewis, Raghavendra, Tetali, and Vempala. Both of the second and third results are optimal, up to constant factors. For the first result, we don't know. Still, it's an open problem. Okay?
You assume that the genus is bounded by constant?
Yeah, if the genus is bounded by
So what is the dependence on, let's say, the genus?
logarithmic.
Oh, okay.
So when it is optimal k versus 2k, so can you replace lambda 2k by, let's say, lambda 3 half k?
Yeah, we can do that, yeah. For any constant greater than 1.
But just the big O, it loses some.
Yeah, if you use 1 plus epsilon, then you do some function of epsilon. In addition to this, our proof is constructive. It basically gives you an algorithm to find S1 up to Sk such that the maximum conductance is at most order of k squared phi k. All of these results are constructive. Okay? We can. So the proof also provides a rigorous justification for a spectral clustering algorithm. For example, it shows that your data or your graph has a good k clustering if and only if lambda k is very close to 0. Okay? Let me tell you a little bit of the proof. Okay? So since I have limited time, I'll try to give you the main ideas. Okay? So for the next 5 to 7 minutes, I'm going to talk about proof ideas. Before saying the ideas, let me first define a continuous relaxation of conductance and then tell you the ideas. Okay? So I'm going to use Rayleigh quotient as the continuous relaxation of the conductance. Okay? For a vector x, Rayleigh quotient is this quantity. Okay? You don't need to understand this. The point is, if our vector x is a 0, 1 function, a 0, 1 vector, then this quantity will be exactly equal to the conductance of the support of x. You can easily check that in this case, the numerator would be exactly the number of edges leaving the support, and the denominator is exactly the summation of the degree of vertices in the support. Okay? So basically the point is, if you could, for example, find the 0, 1 vector minimizing this Rayleigh quotient, that would give us the sparsest cut of a graph. So you cannot do it. It's a hard problem. Okay? So now let's see what are the optimizers of this continuous relaxation. The nice thing about this is that the optimizers, the minimizers, are exactly the eigenvectors of the normalized Laplacian matrix. After you need to do some normalization by the degrees, but after the normalization, the optimizers are exactly the eigenvectors. In fact, so V1 is the minimizer of this. R of V1 is lambda 1. V2 is the minimizer of the Rayleigh quotient over all vectors that are orthogonal to V1, and so on and so forth. V3 is the one that minimizes over all vectors that are orthogonal to V1 and V2, and so on. Okay, R of V1 is lambda 1, R of V2 is lambda 2, R of Vk is lambda k. So basically, you can think of V1 up to Vk as a k-dimensional orthonormal basis minimizing the Rayleigh quotient. So in other words, you can think of our problem as a rounding problem. So this k-dimensional basis gives us a solution to the continuous relaxation of our k-clustering problem. You want to round it into an integer solution. So how are we going to use this? We're going to use the continuous relaxation by embedding our graph in a high-dimensional space. This is exactly what I did at the very beginning of the talk. Okay? So basically, I map each vertex I to this vector v1 of I, v2 of I, up to vk of I. Okay? So let me show you some example to better understand this. For example, if the graph is just has k connected components, then this spectral embedding maps each connected component to a separate point in this high-dimensional embedding. Each connected component will map to the same point. And you can see clustering will be very easy. Okay? If the graph is a cycle and k is equal to 3, then this spectral embedding gives you exactly the cycle. So what happens in general? In general, this embedding has two important properties which will be crucial for the proof. The first one is that the mapping spreads in the space. The vertices cannot be concentrated in 2, 3 places. They have to spread in the whole space. Okay? Think of the cycle, for example. The second one says that adjacent vertices will map to close points in this high-dimensional embedding. I'm going to say the quantitative version, yeah. So we're going to use the first statement, the first property, to argue that we can choose k disjoint clusters. Because the points are spread in the space, we can choose k disjoint clusters. We use the second property to basically to choose our clusters from groups of close points. Okay, so you see the cycle, for example. So basically, these two make two components of our proof. So what I'm going to do is that in the next two slides, I'm going to tell you about each of these components separately. Okay? So let me first start with the first component and then tell you about the second. So the first component is called the spreading property. Okay? So we prove the following statement. We prove that each narrow cone through the origin has at most essentially 1 over k fraction of the vertices. Okay? Here is the exact quantitative version, but do not need to understand it. The point is, if you look at each cone, it has only 1 over k fraction. So there cannot be too much vertices in one direction. They have to spread in the space. Okay? Now, the way the proof of this goes is through an isotropy property, which shows that if you choose a unit vector in this high-dimensional embedding and project all of the points to this vector, the mass after the projection is exactly 1 over k fraction of the mass before the projection. So basically, all directions look the same. In each direction, you see only 1 over k fraction of the mass. And the proof of these only use the fact that our embedding comes from an orthonormal set of vectors. So we don't use anything special about eigenvectors. Any embedding you give me from an orthonormal set of vectors would satisfy this. Okay? So this was the first component. Now let me tell you about the second component, which is that how we choose these disjoint clusters, k disjoint clusters. Okay? In the previous case, the previous component, I wanted to argue that the vertices cannot be concentrated in 2-3 places, right? Now, if the vertices, in this case, the difficulty is if the vertices is kind of uniformly spread. So in fact, if the vertices are concentrated in k places, I can just return those k clouds, right? And that would give very good solutions. The hard instances, in this case, are those when you have kind of uniform distribution of the vertices in the whole space. Because here you kind of have to, partition these vertices and separate the vertices that are very, very close to each other. And that would make the problem hard. Okay? So in order to argue that we don't cut too many vertices, we use random partitioning of metric spaces. So basically, we randomly partition the space. And because we do it random, each edge will be cut with some very small probability. Okay? So here we use some vast literature on random partitioning of metric spaces using the works of Charikar, Chekuri, Goel, Guha, Plotkin, Gupta, Kratkamar, and Lee. Okay? Now, these random partitionings incur a loss of, that is, a polynomial function of the dimension. Okay? Since we are in k dimension, we get a loss of polynomial in k. Now, if you want to give a better loss, if you want to decrease the loss, the idea is to, as you may guess, is to do dimension reduction, to go from k-dimensional space to log k-dimensional space. But this wasn't an easy task. The reason is that because k can be very much smaller than n, dimension reduction will not preserve many of the pairwise distances. Okay? Nonetheless, we show that it preserves the spreading property and the average edge length with very high probability. And that is what is essential for our proof. Okay. So before finishing this part of the talk, let me compare what we did with the Cheeger's inequality. So in Cheeger's inequality, as I said, we just use the second eigenvector. We basically map the vertices to a line based on the values in the second eigenvector. Now, because this is just one-dimensional embedding, you can test all cuts, okay, and choose the best of them. Here, instead of choosing one eigenvector, we use multiple eigenvectors and map the vertices in a high-dimensional space. Now you can see where the difficulty comes from. You cannot test all of the cuts. There are exponentially many. So basically, we use random partitioning to avoid cutting too many edges. So you can see our proof as a high-dimensional variant of Cheeger's inequality proof. OK, so let me conclude this part of the talk. Cheeger's inequality is one of the fundamental results in spectral graph theory. It has applications in various fields of computer science. We managed to generalize this inequality to higher dimension, to k-way partitionings. Our proof gives a rigorous justification for the spectral clustering algorithms that use multiple eigenvectors. In addition to that, our proof introduces new components that can be used and possibly improve the quality of spectral clustering algorithms. So here is an example that I tried. So say you want to cluster these data points. Okay? Now, I use the original spectral clustering algorithm, and this was what I get. And then I applied the dimension reduction. And this significantly improved the quality. Okay? Note that here I'm not claiming that dimension reduction always gives better answer. I'm just saying this may help in some cases to get better quality solutions. Okay? One reason for that is basically that partitioning in lower dimensional space is easier. Any question? OK, so I'm done with the higher order Cheeger inequality. Now let me talk about improved Cheeger's inequality. First, let me tell you about the tightness of Cheeger's inequality. Okay? It turns out that both sides of the Cheeger's inequality are tight. The left side is tight for a hypercube, and the right side is tight for a cycle. Okay? For a cycle, for example, lambda 2 is 1 over n squared, and a sparsest cut is about 1 over n. Okay? So if it is tight, how can we improve it? Okay? So let's look at the kth eigenvalue of a cycle. It's about k squared over n squared. Okay? Now, you can see that k lambda 2 over root lambda k for a cycle is about root lambda 2. So although root lambda 2 was tight, this is also tight. So basically, we show that this wasn't a coincidence for a cycle. It actually holds for any graph. For every graph G, phi of G is at most order of k lambda 2 over root lambda k. Okay? The importance of this is that this guarantee is achieved by the spectral partitioning algorithm that uses only the second eigenvector. This was very surprising to us, because the spectral partitioning knows nothing about higher eigenvalues and higher eigenvectors. Okay? But still, you can analyze it using the higher eigenvalues and prove better guarantees. So the interesting thing is following. Say, in general, you may have graphs where lambda 2 is very close to 0. Say lambda 2 is 1 over n. Then the original spectral partitioning, the original analysis, would tell you that the solution of a spectral partitioning can be n times worse than the optimum. So it could be very bad. Okay? But here what we say is that although lambda 2 could be very, very small, if I know that lambda k is much, much larger, I still can show, this algorithm gives a very good answer. So this is actually what happens sometimes in practice. So say you want to do image segmentation. Okay? So typically in image segmentation, you have k or k minus 1 objects. Now you construct a graph based on these objects, right? You put a vertex for each pixel and connect them. Now it turns out that the graph that you would construct typically would have very large, like the kth eigenvalue of the graph you construct would typically be very large, would be very close to 1. The reason is that these graphs would look like unions of k expanders. Now, by our analysis, we can argue that phi of g is at most order of k lambda 2. Therefore, the solution of the spectral partitioning algorithm is only order of k times worse than the optimum. So it's actually very close to the optimum. And that is exactly why people use this algorithm in practice and they get very good results. Because many of the practical applications satisfy this property. Okay? So this was what I wanted to say about this result. So basically, you can segment this image and get these objects. Let me tell you very, very little about this last result, like a 2 to 3 minutes, about finding small communities in large social networks. First, let me tell you why I'm interested in finding small communities, and then tell you what we do. So basically, here are the 3 results, the 3 reasons. The first one is that let's go back. Lang, Dasgupta, Mahoney show that, basically do a practical, empirical analysis and argue that best communities in large social networks are very, very small. They have size only about 100. Okay? The second reason is that typically small communities would represent a group of people with similar interest, whereas large communities would correspond to large-scale noun factors, such as age or ethnicity. Okay? And lastly, if you find a partitioning into large communities, if you want to find partitioning into small communities, that would itself give a partitioning into large ones. This is because if you have 2 communities of a small conductance, their union would have a small conductance as well. So basically, you can just combine the small communities and give a partitioning into large communities. So what do we prove? We show the following. We show that for any small community, or for any target T that you would like to find, you can find a set which is slightly larger than T with a guarantee that conductance of S is at most square root of conductance of T. And we can do it very fast, in time proportional to the output size. S could be much smaller than the size of the graph. So this basically improves upon the results of Spillman, Teng, Anderson, Chung, and Lang, and Anderson Press. So basically, these results show that you can do the same thing, but their guarantee has this dependency to the size of the graph, has a root log n dependency to the size of the graph. So we managed to get rid of this dependency and get a guarantee in a sense very similar to what you get from spectral partitioning and Cheeger's inequality. Also, a weaker version of this is proved by Koch and Lau independently. So what we show basically implies that you can get an algorithm that with almost the same guarantee as of the spectral partitioning, but with the advantage that it can be run in sublinear time. Also, our proof gives improved lower bounds on mixing time of random walks that I'm not going to get into. Okay, so let me conclude what I said during this talk. I talked about spectral algorithms, spectral graph algorithms, through the lens of higher eigenvalues. I talked about these 3 generalization and strengthening of Cheeger's inequality in a spectral partitioning algorithm. Our results use developments in high-dimensional geometry. It also develops new techniques and new tools that has been used elsewhere to get new results. For example, we use these techniques to give universal bounds on higher eigenvalues of graphs, give improved approximation algorithms for max cut, mean bisection, and so on. Also prove a new regularity lemma. Okay? I'm not going to talk about these results here. You can ask me offline. All right. So I've worked on approximability of various problems. And here, I wouldn't have time. I mean, I can just give one talk. I cannot tell you about all of this. So let me tell you about approximating traveling salesman problem. OK? So let me remind you of the traveling salesman problem. Say, this may have happened to many of you. You go for a short visit to a new place. Maybe you go for a conference to Seattle. And perhaps in the second day of the conference, you get tired. So you decide to visit some places. Maybe in this case, you want to visit Parker Street, Madison Park, University of Washington, Green Lake, Space Needle. MSR didn't fit here. It was a little farther. But so basically, you do not have unlimited amount of time. You want to head back to the conference as soon as possible. The question is, what is the fastest route to visit all these places? And maybe in this case, this is the fastest route. So this problem is known as a traveling salesman problem. So again, you have a set of places. You want to visit all of them and return back to the starting point. So this problem has many variants. These are, I would say, three of the most important ones. The most famous one is the symmetric TSP, where we assume that the distance function is symmetric. Okay? Going from here to, for example, UW has the same cost of going from UW to here. Okay? Then there's the asymmetric version of TSP, where we don't assume this symmetric property. The distances could be different. This is a generalization of symmetric TSP. And then there is the Euclidean version, where we assume the points are embedded in a plane, and the distance between a pair of points is the Euclidean distance between the corresponding points in the plane. Okay? So let me tell you what we knew, what was the state of the art before our work. There is a 1.5 approximation algorithm by Christofides that hasn't been solved for hasn't been improved for over 35 years. There is a log n approximation by Fries, Galbietti, and Maffioli that, although many people have tried, they only managed to improve the constant in front of the log n. And there was a PTAS, polynomial time approximation scheme, for Euclidean TSP, which means that you can get very close to 1 in polynomial time. Okay? So what did we do? Here is just a summary. We, in a joint work with Saberi and Singh, sitting here, we managed to improve Christofides to 1.5 minus epsilon approximation for a canonical important special case of TSP called graphic TSP. In a joint work with Saberi, Gomez, Madri, and Asadpour, Gomez, Madri, and Saberi, we managed to improve the log n barrier for asymmetric TSP and improve it to log n over log n. Also, in a joint work with Saberi, we managed to give a constant factor approximation for asymmetric TSP on planar graphs. Okay? In addition to that, the proofs of this develop a new technique in algorithm design called rounding by sampling that has been used in for many other problems, many other applications. All right, so in the very limited amount of time it remained, let me very briefly tell you about future. Let me tell you some interesting problems. So here is a theoretical problem. So there is an inherent connection between spectral algorithms and some very hard conjectures in theoretical computer science, unique games conjecture. So let me remind you that here I showed that by higher order Cheeger's inequality, we know phi of k is at most order of root log k lambda k. I told you that this root log k is necessary. You cannot get rid of it. It's tight. Now, Aurora, Barak, and Stewart showed that this root log k is not necessary. It's unnecessary if k is very large. So although for a small k it's necessary, if k is polynomial in n, it is not necessary. You can get rid of it. And using that, they managed to get some improvement. Now, the point is, if you can improve this result a little bit from n to the epsilon to, say, 2 to the root log n, then that would refute the unique games conjecture. And it could possibly imply to many advances in designing approximation algorithms for many problems like max cut, vertex cover, and so on. Okay. Here is another problem. I'm also very interested in online optimization. And I've done some work in this direction. You can ask me offline. But here is an interesting problem. So let me remind you that in online optimization, the difficulty is that we don't have full access to the input. Okay? The input arrives online, and we have to decide irrevocably once we see a new element. Okay? So what we do usually is that we compare ourselves with the optimum offline algorithm. Okay? I call this the information god. Okay? This is the algorithm that has the full knowledge of the input. Okay? Now, usually there is an information theoretic barrier. Because we don't have full information of the input, we cannot get very close to this information god. Okay? Now, ideally, we would like to compare ourselves to the optimum online algorithm. This is the algorithm with the same knowledge as us, but with the advantage that it can be run, that it has unlimited computational power. I call this one the computation god. Okay? Now, it's very easy to see that computation god is always less powerful than the information god because it has less information. It has the same information as ours. So, competing with him is easier. You can hope to get past the information theoretic barrier. Okay? Let me tell you some. Let me be more specific. So, in particular, let's say you have some online optimization problem, and you are given the distribution of the arriving inputs a priori. So you know the distribution. Now, once you know the distribution, you can compute the optimum online algorithm in exponential time. You can write an exponential time dynamic program and compute it. Now, the question would be, how can you approximate this optimum online algorithm in polynomial time? Now, the answers to this question can have a lot of applications in stochastic optimization, for example, in online advertising, or in flight scheduling, many other fields. OK. So let me finish up with this last slide. As a theoretician, I usually think how my research can impact practical applications. Okay? I try to have this in mind when I choose my direction of research. So here are two ways that I think a theoretician can be helpful in practice. The first one is to design new tools and new techniques that can give us, that can help other people, other algorithms, other heuristics in practice. And the second one is to prove a rigorous justification for many of the heuristics that people use in practice, but I don't have any idea why these are working. Right? OK, let me stop here, and I would be happy to have your questions.
So, like, if someone mentioned that higher eigenvalues, like how much time does it take? Like, if I want to get, let's say, the first k eigen, it's k times
k times n. You can do it. Yeah. I mean, theoretically, you need to use this linear Laplacian solvers, and using that you can do it in k times n. Yeah.
Some polynomial factors.
Yeah, no polynomial factors.
So the improved Cheeger inequality, in what way you want to use it?
So the point is you can use this to get algorithms to get very fast algorithms for low threshold rank graphs. So these graphs are a generalization of expanders. So in expanders you have the property that the second eigenvalue is very close to 1. Here the first k eigenvalue could be small, but the k plus 1 eigenvalue is very close to 1. Now there is many other papers that study many algorithms on low threshold rank graphs. You can use sophisticated STPs or the Lasserre hierarchy to study them. But here, what we wanted to say is that you can use this very simple algorithm, just use the second eigenvalue, second eigenvector, to give very good performance for the problems on low threshold rank graphs.
In spectral clustering, I just tried to use it in practice a few times, and I'm always a little bit confused about how to pick the right type of Laplacian matrix, and how connected should my graph be before I compute the eigenvectors. Are there any? Can you give me guidance on those kinds of questions, or are there people working on those kinds of questions?
So
set up the problem.
Right. So here we use one particular Laplacian, like normalized Laplacian. We use the eigenvectors of this. In the literature, I've seen people use different eigenvectors and different normalization. Like there is a very nice survey by Luxembourg, I think, who basically kind of gather different normalization. Like we can use either eigenvectors of normalized Laplacian, or the random walk matrix, or in fact the whole adjacency matrix without doing any normalization. So all three are studied. And
I think part of the question is even when you start with data, how to choose which graph to look at.
Right. How connected should the graph be?
So you connect just to nearest neighbors or further.
Oh, yeah, you gave two examples right away on the first slide, right?
Yeah. So if you want to, so good. So there was two questions. So one question is how you constructed the graph. The second one is once you constructed it, which normalization do you use? This was the question. This was the answer to the normalization. Now for constructing the graph, again, there are many ways. I described two of them. In the first slide, one of them was that to connect the vertices that are close to each other, give some threshold and connect the vertices that are close to each other. The second one is basically construct a complete weighted graph where the weight of each edge is some function of the distance. For example, e to the exponential function of minus distance squared.
Right. Yeah. So both those techniques have a magic number you can pick, right? One is the threshold, and one is the
standard deviation.
Right. So for example, in this paper of Eng, Jordan, Weiss, they argued that what you should do is basically you should try very different thresholds and see what would give you the best answer. But
so there is no somehow.
For example, if you assume your data is from some Gaussian distribution and you may have some prior knowledge and bounds on the variance of the Gaussians, then you can use that.
Or even if you don't, but doesn't this just guessing thing will get you function, right?
Yeah, you can do that as well, but this takes more time. Yeah.
Any other questions? Thank you, Shayan, again.